Our next speaker is Leung. I'm not quite sure about his surname. I should also say that C is probably known to some of us by his previous name or his Christian name, Adrian, but it's C. Jan. No? Yes. And you started off as a PhD student with TED in Reading, and you are now at the Met Office, based here in Reading as well, working on data simulation.
All right, could you hear me well? Good. Yes, so today I'm going to talk about my previous work, not in my PhD, and also not in my current work in Met Office, but the work during my postdoc with Amos Lawless and Nancy Nichols here in Reading, but also collaborating with colleagues at the Met Office, namely Matt Martin and Daniel Lee. So I appreciate that this is the last talk of the day, and indeed the last talk of the workshop, and I promise that it won't be too boring for you. There won't be too many equations. But, well, you can see there's quite a long title. So the talk will be about hybrid ocean DA and a coupled model and a tropical cyclone. So there are a few perspectives in this study, and I would like to start with introducing the problem from the DA approach, because this is what most of you are familiar with. Okay. Right, so I am doing variational DA, so everything is nice, no particle filtering. And I will start with talking about the background error covariance matrix B, and this in variational DA would play a crucial role in determining how information from observations are spread to the unobserved parts of the system. So you can work this out theoretically. And what we're doing is hybrid DA, and what hybrid DA means is to use a background error covariance matrix that combines both climatologically based and parameterized information with information from the latest available ensemble of the day. So you can see that this is a linear combination with the coefficient alpha here, with alpha being between 0 and 1. So having hybrid DA, this would introduce explicit flow dependence into the B matrix. So you can imagine that information from observations can spread in a more realistic way, in a way that is more reflective of the current state of the system. So this hybrid DA approach is very mature in atmospheric part of the system, not in NWEP context, but relatively new in oceans. So what we're doing is to introduce hybrid DA in the ocean and to apply this in a coupled model setting, in coupled numerical weather prediction. And we know that because everything is coupled, by introducing hybrid DA in the ocean, we can also change the representation of the atmosphere. And this is especially the case for tropical cyclones, because in tropical cyclones, the coupling between the air and the ocean is strong, and error structures can be very different from the climatology, which is used to model the existing version of the B matrix. So this will be a case study of a tropical cyclone called Titley, which was active in the Indian Ocean in 2018, and it experienced some rapid intensification the day before it had landfall in the eastern part of India, which is you can see this on the map, and the winds were quite strong, and unfortunately it claimed quite a few lives. So the study will be done first in the ocean, but also later in a coupled numerical weather prediction system. And this is a development version of the Met Office NWP system. So DA is weakly coupled. And what this means is that when we have the background, the trajectory for the background is from a coupled model integration, so it's shared between components. But then once we have that, we do the variational minimizations separately, component by component. So this is a parallel process. Then you glue the analysis increment together to add them to the coupled model. Then you run the next coupled forecast. So this is what I refer to as weakly coupled data assimilation. So because of that, the immediate impact of observations would be limited to the own component. So observations for the ocean can only immediately influence the ocean. It can't change the atmosphere. But if we cycle the model, if we cycle the data assimilation system, then we'll start to see some cross-component influence. So because the change that I'm going to make is mainly in the ocean component, so I'm going to talk a bit more about that component. So the model is NEMO, and it is at about 1/4 of a degree horizontal resolution, which is about 25 kilometers in the Bay of Bengal, and up to 75 vertical levels. And the DA system is called NEMO VAR, which I'm going to show you some details. So it's 3D bar with first guess at appropriate time, or FGAT, and the model variables are temperature, salinity, sea surface height, and horizontal currents. So these are the model variables for NEMO. And to do the assimilation, the control space variables are the temperature, but then we have like everything else being unbalanced. So salinity is a function of temperature plus an unbalanced part, and the sea surface height is a function of temperature and salinity plus an unbalanced part, and so on. So the temperature is the main variable, and then we have the unbalanced salinity, sea surface height, and velocity. And why I have the unbalanced V being in parentheses is that we don't actually have velocity observations. So in practice, the velocity is just freely evolving. So in terms of observations, we assimilate 3 types of observations, broadly speaking. The first is sea surface temperature. So they are mainly from satellites, but also with a few observations from buoys and other like ships and surface-based instruments as well. So there are a lot of observations of sea surface temperature, but only very few in cloudy regions because they don't pass quality check. Then the second type of observations we have is called sea level anomaly, which measures the difference between the sea surface height and some climatology value. And these observations are also measured by satellites, but along some straight tracks. So only directly beneath where a satellite is. And then we have temperature and salinity profiles. So these are the only measurements that measure the ocean beneath the surface. And they go up to 2,000 meters in depth, but horizontally speaking, they are very sparse. So these 3 types of observations are basically what we have in the ocean. And the profiles would set the large-scale density structure of the ocean, and the sea level anomaly observations would constrain the mesoscale, so the smaller scales, and then the sea surface temperature observation would control the behavior in the mixed layer of the ocean. So first of all, ignore the coupled part first. We'll just do some single observation experiments in the ocean. So the theory of variation DA tells us that the analysis increments from assimilating a single direct observation would be proportional to a column of the B matrix. So I don't have much time to go through the notations here, but you can see that the delta X, which is the analysis increment, is some scalar multiplied by BK, which is the column of the B matrix. So in other words, if we do single observation experiment, we will be able to reveal the structure of the background error covariance matrix. So we'll be doing this for different combinations of the hybrid DA with different values of alpha, and also with different types of observations. So we assimilate SST observation and a sea level anomaly observation and also a temperature observation at 100-meter depth, and they are all done separately. And the same experiments are repeated on 2 days, so one before the cyclone is passed and also one while the cyclone is passing. So this will reveal the time-varying nature of the ensemble B matrix. So this ensemble B matrix is computed offline from a separate 37-member ensemble, and they have these localization and correlation length scales, which you can see here. And on the right, you'll see some figures showing the ensemble standard deviation structure from that very ensemble. So these structures will directly inform the background error covariance matrix and also the analysis increments. So you can see in particular on the top right-hand panel that while the cyclone was passing, there's quite a large spread in SST, and this is related to a well-known phenomenon that because cold water is being brought to the surface by the mixing associated with cyclone, and that is a part of the dynamics is difficult to predict, so we have quite a large spread. And you can see the structure beneath the surface as well in the middle and lower plots. So now I'm going to show you some results on, well, first having a single SST observation. And the right-hand side shows you the increment of the sea surface temperature. So from top to bottom, you have the different alpha values, and then the left-hand side is before the cyclone passed, and the right-hand side is after the cyclone is passing. The increment is much weaker as alpha increases, as you can see, and indeed it's much smaller spread of SST in the ensemble compared to the just the modeled background error covariance matrix. But after the cyclone passed, the increment associated with BNs is more concentrated as the localization scale is shorter than the long length scale of the modeled B matrix. So you can see, like, if you compare panel G and H, you can see the direct effect of having a much larger variance in the ensemble. And then we have a sea level anomaly observation. So the plots show you the temperature increment as a cross section. So it shows you the structure beneath the surface. And you see that there is more anisotropic and vertically less uniform structure as the ensemble is being given more weight. And indeed, you can see some tilting, a bit of tilting on the 9th of October before the cyclone is passing, and then more tilting on the 11th of October. So this is, again, because the ensemble has a larger spread. And in the case of the 11th of October, the ensemble spread is actually larger in the ensemble than the modeled value. So you can see larger increments in the in panel H. And finally, we have a subsurface temperature observation. So again, I show you the subsurface temperature increment along that cross section, and this time the structure is very different. You can see in terms of the horizontal and vertical scales, the how the increment changes as the alpha is varied. So you can see that on the 9th of October, the BNs can also robustly capture a separation between the mixed layer and the waters beneath the mixed layer, which is expected of the ocean. But the BNs does not inherently have this property, while the B mod does. On the 11th of October, there is no such separation, but it could be expected because the cyclone's cold wave would draw waters from deep ocean onto the surface. So there's much less separation between the two parts of the ocean. And the maximum increment in panel H, you can see, is actually quite far from the observation, and that is driven by the ensemble standard deviation. So that part of the ocean where you can see the maximum, the deepest red color, has a large standard deviation, and that's why it drives the phenomenon you can see here. So also, you can see the impact of the correlation and localization length scale being quite clearly visible in the variation of the horizontal and vertical extents that you can see here. So I'll briefly talk about the couple experiments. The ocean is now coupled to a rather low resolution atmospheric model. And we do two deterministic experiments. So a control experiment with no ensemble contribution in the DA in the ocean, and also a hybrid experiment. And the setups are identical apart from just the B matrix for the ocean. And we add some ensemble inflation for the oceanic BNs just to maintain the spread. And we do 6-hourly data assimilation cycling. But the information for the ocean BNs is only updated every 24 hours because this is the frequency of information we have. We don't have any information at shorter intervals. So we spin up the model for 2 weeks before the period where cyclone was active. And I have to note that we are not attempting to compare the forecast and analysis accuracies, because both experiments, as they turn out, are quite bad because of the low atmospheric resolution. So this is not a quantitative assessment. It's not an assessment against the operational analysis, but it is a qualitative way of understanding what differences can be brought by the different background area covariates in the ocean. So we'll first look at the impacts within the ocean. On the right-hand side, on the top, you can see that there's a dipole of temperature difference between the two experiments developing for a week running up to the time of the tropical cyclone. So we've done some further studies and found that the formation of the dipole is actually linked to some SLA sea level anomaly altimeter tracks measuring the sea level heights that day. That was a week before the formation of the cyclone. So we can see that the impact of different data assimilation schemes can be quite long-lasting because the subsurface ocean has a long memory. And this shows that the role of the ocean in representing tropical cyclones is not limited to just the sea surface temperature or like the top mixed layer of the ocean, but also the subsurface fields can contribute to these sort of differences. And now I'll show you the impacts on the atmosphere and the sea surface temperature. So the cyclone intensifies faster in the control run, as you can see in the panel A on the top. So at a particular time. So this is during a 6-hour window on the 10th of October. So the cyclone is much stronger in the control run than in the hybrid. And this is caused by the different descriptions of the air-sea coupling during the incremental analysis updating period after the assimilation. And we know that because stronger winds in the control run would mean an enhanced mixing in the upper ocean, and that would bring cooler subsurface waters up to the surface and then lower the sea surface temperature. And this sea surface temperature difference can also be caused directly by different assimilations of this SST observation itself, and also the subsurface dipole of temperature difference that we have just mentioned. So you can see quite a lot of factors, driving these differences on the sea surface temperature and also the atmospheric representation of the cyclone as well, especially in the timing of the intensification of the cyclone. So, as a summary, we have seen that hybrid B matrix makes the analysis increments more flow dependent. And the increments are generally more irregular than those of the model B matrix, as we saw in the single observation experiments, and they can be quite sensitive to the spread of the ensemble, which is important, which highlights that it is important to model the ensemble spread right. In coupled models, the hybrid B matrix in the ocean can change the representation of a tropical cyclone because the subsurface differences can be brought to the surface through the mixing associated with the strong surface winds. And precisely because the subsurface has a long memory, the differences in the representation of tropical cyclones may even predate the tropical cyclone itself and therefore be unrelated to it. So you can have things that come well before the formation of tropical cyclone, and that would affect how the tropical cyclone is being represented after a week. We have also seen some SST differences, and this is a result of a few intertwining mechanisms. First of all, the different ways of assimilating the SST observations themselves, and also how the subsurface differences are brought to the surface, and also how the air and sea interact in the model, which could lead to the discrepancy in the tropical cyclone's central pressure and therefore the different representations of the cold wave. So all in all, the effects of hybrid B in the ocean can be very complex. This is the main message you take home when tropical cyclones are modeled in a coupled approach. And all parts of the ocean, not just the surface or the mixed layer, can contribute to this. So that's all I want to say today. If you're interested in the work, you can have a look at the paper which has recently been published in the QJ. Thank you.
Thank you, Celia, Jan. We have time for questions.
The last slide, you say all parts of the ocean can contribute, but I mean, when I understood you correctly, you can only observe a very thin upper layer. Right? Anything else, what the NEMO model does is completely, I mean, that's good.
Well, we do have observations down, but very sparse. So down to, like, through the whole ocean column, down to 2,000 meters. But these profiles observations are very sparse, so you don't.
Is it really changing the dynamics of your model? I mean, you're locally adjusting something.
Well, but these would set the large-scale structure, so they actually are quite powerful in determining the large-scale structure of the ocean.
So the very long range.
I would say in the synoptic scale.
Okay.
So like a few hundreds of kilometers. So
you're saying that even though they're very sparse, they're sufficient to really constrain the dynamics of the subsurface?
The large-scale dynamics, yes. Okay. So this is a result from a paper 8 years ago by one of my co-authors, Stan Lee, and he did a study on finding out the complementarity of the role of the observation, different types of observation for ocean DA. And that's what he found.
Okay. Thank you.
Is there any more questions? Yes.
Comment on the question. Do you know if so this observation that you have on the vertical, of course, they're very localized because it's just not much you can do. But does it matter? Like, is it independent of where you actually having that, or having some local observation on one part of the ocean is going to bring you more information if you have it on other parts of the ocean?
Well, the observations are independent, and we assume them to be uncorrelated, which for most cases is a fair assumption.
Between themselves, yes, but so it doesn't matter if it's on a space of the ocean or another point of the ocean, basically. It's not the one that's going to carry you more information. I don't know, maybe because there is a current in that particular location, so you might get more information if you get that observation from there on that spot. And I wonder if the DA could actually see that if you were just to provide the observations depending on the location?
But the observations are not placed strategically after a particular day phenomenon. So we just assimilate what we have.
Yeah, fair enough.
So yeah, of course it would be nice. So if we see, say, a tropical cyclone, we put more observations there. But in practice, we don't have the time to just switch, like put all the resource just because there's a tropical cyclone.
Of course, it's not really that bad thing, but
Okay.
Sorry, do you need the mic still?
no.
I had a question. How you might have actually said this, but how does one typically set the alpha, the mixing ratio between the background matrices? What's the
So
way of doing this?
In our experiments, it's just, we just set the numbers ourselves, and in operational practice, or like at least the vision that we're going to do in the future would be to have the alpha being tuned. So we tried a few different alphas and see the performance. There's no ideal way of like theoretically tuning this alpha to the best possible results, and we can't know this a priori.
So what is the value you have taken for these experiments?
Well, for the coupled experiments, it's 0.8. So 0.8 given to the ensemble and 0.2 given to the parameterized covariances.
Thank you.
Okay, any more questions? That's not the case, then thank you again. See you. And I'll hand over to the organizers.
Yeah, so I don't know.
Thank you very much, all.
Thank you very much.
And thanks to all the speaker of the day.
Let's go see.
And all the participants of the program and the other workshop and the previous workshop and
The scientific committee, Pauline, our administrator.
the Newton Institute, not to forget it.
Exactly.
Thanks
So-
for your patience with hiccups that might have happened in the organization, emails and so on, that we will try our best at all levels, and I hope this was a good experience for all of you, and that you took a lot of good ideas and scientific insights. I certainly did.
So we have the room still for the rest of the day. There's actually also fresh coffee there. There are even cupcakes. It's something that I haven't seen before. So even on the last day, we have been able to bring in a variety, a new twist to the workshop. You can, I think, stay here as long as you possibly want,
Until 6.
until we are kicked out, which is still a while from now. I certainly don't have anything to wrap up, but I do want to share a kind of personal message. So I think that, so we had in excess of kind of 50 participants, and everyone would presumably could add a dimension to any wrap-up or summary of this workshop. So it would be preposterous, I think, if I said something about this. But I think something that struck me during the second workshop in particular was that, so we had a very, very large variety of people coming from very, very different backgrounds. And what struck me as very positive was that each and everyone made a very, very strong effort to make the talk as accessible as possible. I mean, for instance, yeah, it is clear that, within half an hour talk, we can't get into all the depths of, let's say, Dan Christian's research agenda. No, this is clear. You tried you just because you were sitting there. So I can single other people out. So there were colleagues who sent emails to me beforehand asking whether what they wanted to talk about, what they were proposing, would be appropriate for this audience. And I remember, for instance, Chiara saying to me in an email what she also said at the beginning of the talk, that she doesn't have any new results to present, but that she would like to give an impression of what is the plan at the Met Office for the future. And I said, of course, this is appropriate, because what we want to know is about kind of open problems and outstanding problems in operational weather forecasting and so on. And I think for this audience, talks like that, they were probably even more interesting than talks along the lines of, you know, we have made this and that experiment and this and that was the outcome and that's it. So from that perspective, I think the interdisciplinary aspect of this workshop, I think we, thanks to all of you, we met the objectives. Let's put it this way. This is my very personal impression. Thank you all.
I mean, I've been here only for 2 days. Yes, I mean, it was a fantastic 2 days, for me at least.
Thank you very much. So let's have some.
And you probably have received, an email from the Newton Institute asking for feedback. So you have the time to get that email. It will help us and of course the Newton Institute because they would like to redo some program like that.
And us is not only us organizers, but you yourself, because you know you help the community by helping the people who are running the Newton Institute, obviously.
Exactly.
If anyone has a key for an office at the math department, please, can I have them, or I'm responsible for this, can I have them back? You don't have to give back the cards that have your picture on it, but you do have to please give back the cards for JJT 222, okay? This applies only to people who have been here for the program, okay?
And you can also leave these things if you don't want them as souvenirs. Just leave them on the table.
But you can, of course, also take them as souvenirs.
You can, of course. Okay.
Thank you.